So unit 5, the random process, the spectral characteristics. Okay. So in the unit 4, what we have discussed, we have obtained the characteristics of random process using correlation, covariance, autocorrelation, cross correlation, autocovariance, cross covariance. Okay. Correlation coefficient, all this we have used. No? So we are in the unit 4, we have used correlation, covariance. These are the characteristics of random process in time domain. Okay. So this will give you what? This will give us the characteristics of random process in time domain. Okay. So time domain, what is another name for time domain? Time domain is also called spatial domain. Okay. So in the spatial domain, if you want to find the characteristics of a random process, what are the parameters we use? We use correlation, covariance, mean. Okay. And we also use what is that? Or correlation coefficient. All this. These are the characteristics of random process in the time domain. Okay. Now here we are finding the characteristics of the random process in frequency domain. What is spectral characteristics? Spectral characteristics means that is frequency domain. Spectral name it means that it is frequency domain. So if you are finding the characteristics in the frequency domain, means that is called spectral characteristics. Okay. So here this what are the spectral characteristics? Here is power spectral density, cross power spectral density. Power spectral density are the spectral characteristics. Okay. So now we will discuss what is power density spectrum. So it is one of the characteristics of random process in frequency domain or spectral characteristics of random process. Okay. Power density spectrum, or it is also called power spectral density. Both are the same one. Power spectral density or power density spectrum. The both are same. Okay. So here what is that? If you take the random process x of t, x of t is a random process. So if you just observe the magnitude of random process, it is varying randomly. So the magnitude will be varying randomly. So from the Dirichlet conditions, we know that if the signal is does not have minimum number of, okay, so it should have minimum number of minimum and maximum over one interval, yes or no? So if it is not having minimum number of minima and maxima over one interval, you cannot find the Fourier transform. Okay. So for x of t, we cannot apply the Fourier transform because x of t does not satisfy Dirichlet conditions. When we can apply Fourier transform, if you take any random process that satisfies Dirichlet condition, for that random process we can apply Fourier transform. Since x of t amplitude is varying randomly, so it does not satisfy Dirichlet condition, we cannot apply Fourier transform. Okay. So that is why what we do here, we use autocorrelation function. Okay. So we have to find out autocorrelation function of x of t. So if you are finding autocorrelation function of x of t, it will be having some definite shape so that we can apply Fourier transform. Okay. So if you are applying Fourier transform to the autocorrelation function of x of t, that is called power density spectrum or power spectral density. Okay. Now we will see the definition. What is the definition of power spectral density? Spectral density is that power spectral density is nothing but the Fourier transform of autocorrelation function of x of t. Okay. So it is Fourier transform of autocorrelation function of x of t is called power spectral density spectrum. Okay. So it is say here Rx of is autocorrelation function of x of t. Then what is your power spectral density? How do we denote here? This we denote it as Rx of omega. So when you apply Fourier transform, the signal will be transformed to frequency domain omega here. So what is the formula? formula. It is integral minus infinity to plus infinity r xx of tau e power minus j omega tau d tau.